Okay, let's begin our session today. So today we'll talk about derivatives. Then we will talk about maximum, minimum, various approximations, then rules of differentiations. Then we will touch upon the various necessity and the sufficient condition of existence of minima and maxima. They play a very important role in the field of optimization, where we have a problem and we want to know what is the best configuration so that we can minimize or maximize our cost function. Then we will see various theorems such as Rolle's theorems and the Lagrangian mean value theorem. Then we will touch upon the concept called as monotone functions. What do we mean by monotonic functions? They are basically increasing, decreasing functions. Then we will see what do we mean by inverse function, and if a function has certain properties, how do they translate in the case of inverse function? So we'll see them. So I have left a blank space. I'll continue it. And then at the end, we'll talk about the one of the most important mathematical tools, that is numerical analysis. The idea is that you might have a function, for example, here. This not might be solvable exactly through pen and paper. For example, you could solve a linear equation, quadratic equation, cubic equation. At best, you can go up to degree 5 polynomial to solve this equation, and you can get up some formula. But there is a theorem proposed by Gallon. It says that when you have a polynomial which has degree more than 5, then you cannot solve that that equation just using pen and paper. You cannot avoid certs. Basically, you cannot avoid some irrational numbers. You have to take account to them. So one of the best techniques to calculate those numbers is through numerical analysis. So basically, they are iterative techniques, and we will see like how this techniques works and how we eventually end up with an answer. So let me begin with our first property, that is derivative. So the word derivative basically means it changes and records the changes in the function. Derivative basically records the changes and see how function changes when we change a parameter. In this case, it's the input, right? If we change an input and we just wanted to see if we increase my input to certain value, so what is the corresponding change do I see in the function? And and that ratio is what we call as a rate of change. uh, you have seen this concept a lot when you have studied something called as velocity, acceleration. Those are also an example of derivatives, where basically you see some quantity like speed, right? For example, we have a quantity called as speed, which is basically distance upon time, right? And the way you calculate the distance is basically you see basically the change in position. Let's say you were in some position x2 in the final, and you started with position x1, and the time it took for you to go from x1, let's say, to x2. Let's say you started with time t1 and you end that particular path. You took this path and it is this final point at time t2. So you calculate this difference, the ratio of these two differences, and which gives you basically an average speed, right? So the derivative also calculates a speed, for example, in this case, but they don't calculate average speed. Basically, they calculate something called as instantaneous speed. So the word itself, instantaneous, says that it gives you the speed at that particular time instant. For example, if I'm interested to know what is my speed at this particular point through my journey, like this exact particular point. Let's say the time was some t prime. Okay, so I'm interested in the speed at that particular time. So how do we calculate this? So your usual this technique won't work in this case, right? So you have to come up with a different way. And the method is to basically calculating something called as a derivative. So derivative basically records the instantaneous speed at various instances. So for in this case, we see that the instantaneous speed, which is dx over dt. For those who know, we write instantaneous speed. Oh, sorry, spelling mistake there. So it turns out that the instantaneous speed turns out to be a derivative of position with respect to time. And we just want to understand why we do have this particular quantity. That's the question. Most of us do know that this happens. If you have a function, let's say you know what is the position with a given time, and someone asks you what is speed, you just simply go and calculate this quantity. That's it. And you get something called as speed as a velocity of time. I mean as a function of time, which is something called as this. And if someone asks you what is acceleration, then you basically take another derivative. Okay. So we know that we do take derivatives, but why do we take derivatives? That's the question. And that's a fundamental question we want to answer over here. So the idea of this derivative basically boils down to the fact that we first start with something called as an average slope. And since to calculate an average slope, you need 2 points. That is your initial point. Let's say you started from here, and the final point is basically this. Let's say you started from here and ended here. Okay, and you basically start calculating something called as an average speed, like over here. This just calculate what is the difference between the distance between them, and you take a difference in time. So what do you get? You get something called as an average speed. So if I just wanted to understand what is my speed exactly at 1, what do? You just slide this point, this final point, as close as possible to 1, and you keep doing that. Okay, let's say you have all the data and everything, you know where all my positions are, you know what where all my everything is there. Just go on sliding this point along this path, because this path is basically a function, right? And this, you have the data for this. There is no ambiguity in that. What is this function, that's clear. So you can calculate what is the value here, you can value here, you can take the difference between the values, take the ratio with the difference in the x. Now the way you can get closer to this point 1 is by cutting down this interval, right? If you make this interval as short as possible, then this point will get slide more towards 1. So basically what you do, you reduce this h as small as possible. And the best you can go is that when you take this h tends to 0, that's the best, right? Because the moment your h becomes tends to 0, this point is basically approaches to this point. So what happens, basically the line which you had this earlier, which was the chord of this curve, right? For example, if you talk about this curve, with respect to this curve, this line is just a chord, right? Because it intersects at 2 different points. So what do you want to make? We want to make this chord as a tangent to that particular point to which we are interested to calculate the instantaneous slope. So that's the idea here. And the way we can do that by reducing this h distance. This h is basically tells you the distance between this interval, I mean the distance between these points. So that's how we try to get something called as instantaneous, because my idea of instantaneous will be more clear and good if my gap between them is as small as possible. Okay, the gap between them things. Just a minute. Okay, so from here I show you that what we are trying to do here. We are basically taking this to point 2 as close as to the point 1 by reducing the gap over here, because this points corresponds to these values. So so when we are calculating derivatives, we assume some properties of the function. We assume that the function is defined from R to R, and the reason we choose this assumption that so that we don't have to worry about domain and all. Okay, because we know that open interval has a problem when it comes to the boundary, right? So to avoid that problem and just to give you a general idea of what is called as derivative, because derivatives don't much depend on our intervals, right? Over here. So to avoid every special cases, we just take a general function which is defined from real to real, and we assume the function is continuous. If the function is not continuous, then that's a problem. The reason is that you might have jumps, and since there are jumps, then you cannot define something called as rate of change, right? Because that will give you something a nonsense answer. I can give you an example here. For example, I had this function over here, and let's say there is a jump here. Then you cannot define something called as a rate. Let's say example at x equal to a, we had a jump, and here's the function is defined. So over here, function is not differentiable. The issue is that uh, if you try to if you try to calculate the slope to the left and slope to the right, though the values of both the slope match, though the values of this and this same, but you can see in between you still have a problem. And the reason why it is not discontinuous, the reason why it is not differentiable, because this is not continuous. So we assume that the function is continuous. Okay. Then we talk about the next level of property, that is called differentiability. So, and one important point. Yeah. Anyone have a question? See, there is one concept called as continuity, which we discussed earlier, and there is another concept called as differentiability, which we will discuss now. Thing is that differentiability implies if your function is differentiable, then you can directly claim that my function is continuous at that point. But if your function is continuous, that not necessarily the function is differentiable. Okay, I can give you one example why uh, this double implies statement don't work. If a function is differentiable, you can directly write my function is continuous, but vice versa is not always possible. I can give one small example. In this case, let's say I have this function f of x equal to mod of x minus a. Okay, what do I see that this particular kind of a graph over here of x equal to a. So if I check my continuity at x equal to a, that's true. My function is continuous. We can see from here as well, right? The reason is if you see the values just left to the a and the values just right to the value match, and also it value and also the value of function at that particular point also match. Basically, what do we see that left hand limit is equal to the right hand limit over here, and it's also equal to the f of a. So there is no question, there is no problem in the continuity in this case. Okay, there is no problem in the continuity. But if I try to calculate the differentiability, whether this function is differentiable at x equal to a, and that turns out to be that's not differentiable. And the biggest reason is that if we try to calculate slope here, here just left with respect to x equal to a, we have a line for which the slope is -1. And you will see just right to the x equal to a point, we have line which has slope equal to +1. So that's why you cannot give, or you can, if you, that's why you cannot assign any value of slope at x equal to a, because that's an indeterministic problem. Like you cannot know which slope it is. Basically, you cannot define any slope over here. So if we talk about the something called as f dash of x, in this case, it turns out to be plus 1 minus 1. Plus 1 in the case when we have x greater than 0, and minus 1 in the case of x less than 0. And what you see that f dash x, let me write this way. I mean, the derivative at x is not defined. Okay, hope to everybody got the idea, like why continuity doesn't imply that your function is differentiable. Why the differentiable, but your differentiability imply that your function is continuous. Here I have given you an example in which the function is neither continuous nor differentiable. And you can also see this statement in this way. Like, in order to the function to be differentiable, the first basic criteria is that the function must be continuous. At least it should be continuous. If your function is not continuous, then you can immediately write down your function is not differentiable. Let me write down over here. If function is not continuous, then you can immediately imply function is not differentiable. You can immediately imply. And the vice versa statement, that if function is not differentiable, that doesn't imply, let me strike it off with a different color. That doesn't imply that my function is continuous. Function is not continuous. I can show you that in this diagram over here. Over here, the function is not continuous. The function is continuous at that x equal to a, but the function is not differentiable. So we see that this holds, right? The function is not differentiable. That doesn't mean, right? I just showed you an counter example here. But over here we can see, if the function is not continuous, then definitely that's not differentiable. The idea is that you can have a slope on the left, you can also have a slope on the right, but you cannot define slope over here, because you don't define something called as slope of an isolated point, right? You cannot write down slope, because the definition of slope is, let me also give you what do you mean by slope. Let's say I have something called as 2 point, right? Let's, and this is your x, and let's say this is your x plus h. The correspondingly you have values of the function here, and the way we define slope at x equals to a, for example, let's say this is a, just to be more precise. So the way we write down this is basically we calculate this limit h tends to 0, a plus h minus f of a over h, right? Because this quantity is what basically calculates the change in the y, right? The change which you are interested. This might, let's say this might be your position sum, and this basically tells you the time interval you took go from initial point to final point. So, and in order to be a precise slope at x equal to a, I want that time interval to be as small as possible. And you can see that in this case, the kind of indeterminate form is basically 0 by 0. So this 0 by 0 can take any value. It depends on what kind of structure it's there inside. So this is what actually the definition of. So is there any questions so far? Like, should I focus on some other point? If there is no question, just give me thumbs up so that I can move forward. Because now I just want to make you clear that if a function is derivative and the derivative of function exists, that means the determinant, I mean, so the limit, this limit should also exist. If I say a slope exists, if I say a derivative exists, a slope derivative is the same word. Okay. So whenever someone tells you what is a derivative, it just means to say slope. And the idea is that the derivative, something called as an instantaneous idea. It talks about an instantaneous point at a given point. But the slope can be defined for a given point, let's say at a given point, and the slope can also be an average quantity. Like for example, uh, okay, like in this case itself. No, let me write another diagram here. Let me first tell you what do you mean by average versus instantaneous. Average versus, let's say this is your x equal to a, and this is your x equal to b. The correspondingly you have a value f of a, and this is your f of b, and let's say this is some function f of x. Okay, and the function is defined from some real to real, just to avoid any ambiguity of continuity and everything. So you have a very regular function. Regular, that means function is defined everywhere, continuous everywhere, and also differentiable. That's what we call something called as a regular function. If someone tells you what do you mean by a regular function, I mean defined, I mean it's defined, continuous, and differentiable. I mean at least first order. mm, I'll tell you what do I mean by first order, second order, and all. The idea is that the first derivative exists. You also have something called as higher order derivative. For example, this is your first order derivative. You might also have this kind of a derivative, which is basically, this quantity basically tells you that you again take a derivative of a derivative. Okay. This is the derivative quantity which you calculate. Just again take another derivative. So this basically gives you this. So this is what something called as a first order. And this is something called as second order. And if someone talks about what do you mean by nth order, so nth order is just taking nth power. It's not power actually, it's an operation. You need to be careful by saying it's a power. It's not a power, it's an operation. This basically tells you that you have taken derivative twice. This tells you that you have taken this operation twice. So this is an operation. This is not like a power thing. Okay. So if someone writes that Tn over dt, some this type, right? That means you're basically taking this operation. You're basically taking this derivative operation nth times. Nth times. Okay. And I hope this small n is natural here. We have something called as fractional derivative, something called as fractional derivative. We are not interested to know what are they. We just interested in something called as this kind of a derivatives. So don't worry about that. So when someone talks about something called as regular function, so this idea should be there in your head. Over here I've just took a regular function. uh, so here I'm basically trying to calculate something called as an average slope. Basically this is your initial point and final point, and I'll just write what do you mean by an average slope here. So the average slope turns out to be f of b minus f of a, b minus a. Okay, and if I just want to calculate what are my instantaneous slope, so basically we define an instantaneous slope for a given point. Let's say this is my point. I just want to calculate what is an instantaneous slope. So that turns out to be instantaneous slope is just a tangent to that point. Slope of the tangent, I mean to say. Slope of tangent at that point. I mean to say. This notation basically means at that. या फिर at the rating. That is also true. And this basically just tells you the usual, your usual delta y over delta x. Basically your y1 minus y2. I won't write here. This is your usual y2 minus y1 upon x2 minus x1. So this basically tells you the slope of chord passing through both points. To define something called as an average slope, we need 2 points here. Okay, and to define something called as instantaneous slope, it is defined for a single point, 1 point. As far as two-dimensional geometry is concerned, we are doing everything in a page. Okay, so we don't have any other dimension to work with. So that's the basic idea of something called as an average slope, instantaneous slope. uh, as I've wrote, that instantaneous slope is just a tangent, slope of the tangent at that point. It turns out to be, let me draw it with a red color, that turns out to be this kind of a line. Okay, and let's say this is some x equal to c. So what do we see, that the slope is basically your f derivative, basically. Yeah. Okay, and over here the slope is this. Hopefully everybody uh, has a clear understanding of this right now. Can we move forward? Is there any question? Is there
No.
any? Oh, that's good. So now I just want to go to an idea, something called as epsilon delta notation. This is known as epsilon delta notation, or you can say definition of differentiability. Okay, so the idea behind this definition is that you define an interval just like as before. Okay, because we see that the definition of the derivative can seen as has to be something called as existence of limit, and we have did and definition for the limits. We had an idea that when limit exists, so how can we write that definition? Let me give you an example here. Let's say we did this idea when limit extends to a, we're just trying to see, and turns out to be some L. So the way we write down the definition is that because I'm claiming that this limit exists and that is equal to L. So the way we write that for all epsilon greater than 0, there exists an interval. This interval is to basically tell you that I can always give you an interval around L, okay? And this interval will basically I will define for this, for the inputs, okay? So the idea is that you give me an interval, you you give me an interval, I can always come up with an interval, I can always construct an interval around x equal to a, such that if I try to calculate the values in that neighborhood, it turns out to be very close to this limit value. So this is how I write, such that the mod of fx minus L less than epsilon for all x minus a, this, right? So everything is same, exact same, just in the case of everything is same, the only difference is that, over here we are replacing this with something called as this, okay? And yeah, this exactly, and you are replacing this with something called as this. The whole definition just translates, because we were trying to find the limit of this, right? And we were checking the limit value, is that limit value is close to this. So I can always define this kind of a definition here. You give me an interval, I can always come up with the delta. Actually, there is a mistake here, I'm sorry, this is not delta, it's h here. So here basically h also works as an interval here, as of what I have shown you in this diagram here, okay? Because if you see, the length of the interval is h, and in this definition also, this lambda captures the same idea. It basically calculates the length of the, the width of this interval. Basically the way you can construct a neighborhood. So over here basically I can always construct a neighborhood according to your given tolerance limit. This is what I call as a tolerance limit, or something called as a confidence, such that if I try to calculate the limit for this limit value will be close to this value, right? And that closeness is defined in the terms of this epsilon. Hopefully everybody got the idea of this definition, like what this definition is trying to tell you. But the catch is, your input, your width should be bounded as well, according to this idea. So basically this what tells you my neighborhood. This is my neighborhood around this interval over here, sorry, yeah, this is what my neighborhood is, this exactly speaking. And this idea basically captures the neighborhood around this particular limit, and the neighborhood is defined, characterized in the terms of this epsilon. That's the idea. So I'm moving forward again. What I'll do, I'll just take this inequality, and I'm assuming this is true. This is always true. I'm just assuming we are only interested in such kind of an intervals, or such kind of a neighborhood, and I'm just try to do some manipulation in this inequality, because I just wanted to come up with an approximate solution. I might not be able to know, right, the value of a point. Let's say, so this might sound confusing, let me clear this up. Let's say I know what is the value over here, okay, like over here I'm talking, okay, but I don't know what is the value at this point. I don't know. I know this, and since I just know the derivative at each and every point, because of this, because I just only have to calculate this, right? So just if I just take a simple derivative, I just know what is this function is, okay? I know what is the value at this point, but I don't know what is the value just, not just, I would say, at this some other point on the function. I just don't know, okay? So I want to estimate the value of this point. And the way you can estimate the value at this point, either going through very rigorous calculations, or you can have an approximation, and your approximation will be more good and clear the more these points are close to each other. So I'm just claiming you something. I'll prove what I'm trying to say here. uh before before proceeding, before I proceed, I just want to make sure that, does everyone identify this what I have written here? Everybody know what is this? Can anyone help me? What is this written? Because this is something important. Like, it's very very important. I hope everybody know this. Yeah, there's a Taylor series. Yes, Taylor series in one dimension for one parameter, and that is also called as Maclaurin series. Yes. So the idea is that using this Taylor series also, we can approximate values. For example, because I don't want to miss this, so I thought let's discuss now itself. Let's say this was your function, right? F of x. Let's say, and you know what is the value at this point. Let's say at x, and the value over here is just fx, and I gave you the task to estimate the value of this, where let's say this points, I mean this x coordinate at a distance of h, and I'm just telling you what is this value. I don't know. I can give you one simple beautiful example for this. For example, if I tell you I have a something called as under root of 25, which I know the answer is 5. But what if I ask you what is the answer of this root of 26? Can you estimate that for me? So estimating this answer is going to be useful using this Taylor series. As you can see, I know what is the, let's say if I define a function like under root of x, I know what is the answer for this. Sorry, I know what is the answer for this. That's trivial. But I'm asking what is the answer for this. Very similar question, right? So left hand side I just shown you an example. But now I just want to estimate this, right? So this Taylor series will help you. So the Taylor series tells you that the value of this can be written down in this way, in a form of a series. Later I will prove this series, not now. Okay, later I will, in the future classes, I will prove this, how this series comes out. For now, just take this as a formula. Take it as a granted, okay? And this formula works for any distance between them. Let's say these are some distance, right? Some h distance. So the idea is that the value of this can be estimated from this at a given distance, some given horizontal distance h, through this formula. And you notice, if the horizontal distance between the points is very small, if the horizontal distance between these points are very small, then we see that we can approximate these quantities to zero, right? These are very small quantities. Why am I saying that? If these points are very close to each other, for example, the distance is in fraction. Let's say, this h is a, let's say in this case, 0.1. So if I take a square, that will be 0.01. If I take a cube and all, so I can safely, approximate the higher order terms, right? I can easily approximate my third term, fourth term, fifth term, and so on. So what do I see that? I see that I can get an approximate solution here, an approximate answer for this. So this is an approximate answer, and that's why I have used this symbol, approx. So this tells you that what you need to know that is just calculate the value which you know. This is what we know. This is your horizontal distance, and just multiply that horizontal distance with your rate. Rate in the sense derivative at that particular point. And you can see this answer holds as good. I mean, this answer is a good answer when these points are very close to each other. Okay, otherwise we have to go and do some other techniques. That is something called as a derivative. That is something called as integration. Okay. uh, so what I'm trying to say that if these 2 points are close, if these 2 points are too close, I mean close, very close, too close, so you can approximate this as f of x plus h times of f derivative at x. This is something called as first order. This is something called as first order approximation. That's what people use the language here. Okay. So what will be my second order approximation? Maybe these 2 points are not that close, but they are fairly close. Not that close, but fairly close. Then what you can do that you can add an extra term here. Okay, you might be able to ignore higher order terms, but you might not be able to ignore this term. Plus h square of double derivative of x over 2 factorial. This is something called as second order approximation. Now you can notice how am I able to write down this first order, second order. So this comes out from this power. Okay. So if in my approximation the highest power is 2, then I say that second order approximation. This is my first order approximation. And if I just have this is what something called as a zeroth order approximation. I hope everyone is getting the idea, right? I just need one thumbs up so that I can understand the people are getting this level. Okay. uh, is everyone getting what I'm trying to say here? I just need one thumbs up. uh, Now let's say these 2 points are not close. Okay, that's a very big heart for me. Thank you, thank you. So the idea is that let's say now these 2 points are not close at all. Now these 2 points are far, like fairly far, you can say. Now what we can do in this case? Then we have just one method, something called as an integration method. So using an integration, you can calculate now. How do we calculate? Because we know that f dash of x, that's basically you know tells you that how my function is changing, right, with respect to the change in x, where your delta bus goes to 0, some where the point differences between them goes to 0. So what I'll do, I just calculate what is my this delta, small delta fx, which can be written as delta x f dash of x. But here they are very close to 0, right? So basically I can write down this to be some d of f, right? D of fx. This is some d of x. This is f prime x. Then I can add them through integration. Okay. And over here, let's say I started with x equal to a, and I'll end up, because I want to calculate till x equal to b, right? Over here, I'm calculating from x equal to a, right? Because that's d, right? So what do I see here? F of b minus f of a, and over here we just have this derivative, so this integration. So what do you see here? This is your answer. So you can see the knowledge of derivative is important, right? The knowledge of this derivative is important. So if you know the knowledge of the derivative, you can calculate, you can estimate value of function at any point, even if they are too close, far close, no matter how distance they are. You can just calculate, right? Using this simple idea. I hope everybody get this calculation, right? what I'm basically trying to do here. Is anyone having doubt in this step? I would like to answer. If anyone has any doubt, please. So I told you the various instances, right? When the points are very close, you can do this. Let's say the points are close but not that close. Maybe you are cancelling out extra terms. Maybe you have to take this term as well. Maybe you might have to take this term as well. Okay. And what if the points are far apart? Not close, very far, quite far. Then you can do this as well. Okay. That both are true. And I just want to remind you one more thing, that the thing which I have wrote here, this is also true in this case as well. Let's say if you just try to solve this and expand, do something about it, and it turns out that this is actually equal to so basically we have this infinite series basically, and I'm claiming that 1 and 2 are same, so you can do both, whatever you feel. But you understand, like doing this is not a trivial thing, right? Because you have infinite terms to add, right? So you need to understand whether this series converge or not. So we have a different problem here. Whether this series converge, I don't know what it is. We just have to see. I mean, this is not a good way of writing, I would say. So you can understand, using the integration also you can estimate values. But for that, you before have to know the knowledge of derivative. So that's why derivative is important. Because not only it tells you about the slope, but also it estimates. Hope everybody understands this ideas, right? Now let's move forward. So the idea is this. So this is what actually I have wrote here. I just took the same thing, same damn thing, I just put it here, did my cross product and take LCM in the denominator. I found this, and the moment I found this, I can do this. How? Because modulus breaks, right? If anyone has a problem in this understanding, I can tell you that if we have mod of this, this is also equal to this. So basically I have used this property. So that's here, from here to here. And what do I see? That my denominator, I want this limit to be 0, go to 0. And this basically tells you that my this limit, this function, this numerator is bounded by this. So you can have this approximation because of this limit, and once you take this part over here, you will see this red box, and this red box basically again what's your first order approximation is. So the method, the way I showed you over here, this process sometimes becomes very difficult to understand. So that's why I gave you the idea of this Taylor series and Taylor expansion. That's why I give you the idea of this Taylor series, because this is very simple to see. Let me solve this problem for you, which I left, which I didn't complete it. So I started with f of x equal to root x, and my a is 25, but I want to calculate b, which is 26, which can be written as 25 plus 1, which is my a plus h. So you can understand my h is 1. So what I'm saying, that h of b, which is h of 26, is basic approximately this h of 25 plus 1 times f prime 25, right? So what is my f prime x here? 1 over 2 root x. So what do I see that? And this is basically my 5 plus 1 times 1 over 2 root of 25. This is 5 plus 1 over 2 times of 5. And you can see very easily this is 5.1. So what do I see that? My under root of 26 can be approximated as 5.1. So this result is basically my first order result. First order result, you can say. So that's the idea here, and that's how we estimate. So this is what being taught here, and we know there is an error. If we just try to calculate what is the square root of 25, so it was square root 26. That is not equal to 5.1. For sure, that is not equal to 5.1. It is somewhere 5.1 point something push. I don't know exactly, but this is not the exact answer. So definitely we have error. So you can write that error as this, uh, root of 26 minus 5.1, and we can take this difference and we just want this to be less than epsilon. Let's say this is some value, so you can always find this epsilon. You can always find this will basically tells you the confidence. Let's say my exact value was 5.125 for example. I'm just saying for example. So we can see that my difference between this and this is turns out to be 0.025. So I can say that my epsilon turns out to be 0.025. So this is my level of confidence. So this is how sometimes we define the approximation, and this is how we write down. Okay, so let's go to the next part. Next part is basically tells you that the same exact result which I have told earlier. The function is differentiable, then function is also continuous. Let's say you know a function, right? And you were just trying to calculate the derivative just by taking simple way the way you calculate derivative, okay? And this turns out to be this. But when you are taking a derivative, you need to be make sure like what you are doing. Hopefully your function don't contain any bizarre in the sense your function might be discontinuous, your function might be having a jagged point like this, for example, which we discussed above, right? Like this is jagged point, a sharp corner. Hopefully you don't have those points in the function where you are trying to basically blindly calculating this, okay? Like for example, this you calculate this you calculate a derivative of this function from here to here just by taking simple derivative, but you see that when you check for n equal to 0 and x equal to 0, it turns out that derivative don't exist, right? You can easily see that, right? For this parameters, but you see that this is n times 0 power minus 1, which turns out to be 0 by 0. Don't exist, right? So you need to be very careful how you are defining. And there are indeterminate form again, many possibilities. So you need to be very careful while defining your parameters here. So you might be writing in this way that n should be greater than 1, or maybe you can avoid that singularity point by saying x greater than 0. So I'm basically telling you you need to be careful when you're taking derivative. Okay, you might be having such difficulties here. I can give you one example here. Simple example. This mod of x. You can see the slope at the left and the slope at the right are not same. Hence, the slope in the center you cannot define. Okay, you might have a situation in which, let's say you add a double power here, like over here we had single power, let's say there's a three power. What do we see that at the left we see there is a function which has a derivative 0, and on the right we see a function which has a derivative to be 0 again. So we can define as a derivative over here is also 0. So again same thing applies here. Let's say you have a left hand derivative that is equal to the right hand derivative, then we imply the derivative is just this. Okay, and exist. Okay, so that's good idea. But there's an interesting function here. So this function is the important function because this is an oscillatory function. If I just try to make a plot over here, so what do you see that you have an oscillatory term here and you have an algebraic term. So you have basically this asymptote lines at y equal to x and y equal to minus x, and in this you have this oscillations, tight oscillation in the center. I mean, you just open up. For sure, the for sure the limit exists. I can see from here. At the center, limit exists. But what can I claim about my derivative? It turns out that my derivative don't exist. Why? Because my definition of derivative was defined was like this, and we see that over here my final result what I got is basically a limit of a sign in which the argument is 1 over h. So it turns out to be this value, I mean this particular limit is oscillating between -1 to +1 very fast. So this is a very fast oscillating term. So you can see this particular value doesn't converge to any fixed point. That means limit don't exist, right? So that's the reason why we are saying the limit don't exist in this case. Because over here you don't have any unique value. Because I can always construct for any interval. I mean to say for any interval I always have a point which maps to +1 and -1. I mean all the points are not mapping to the same value. That's what I'm trying to say here. So that's why the limit don't exist in this case. But the moment you take an extra power here, you can see over here we just had power 1. But over here we have power 2. What happens when you do this square? This actually acts some kind of a regularization. Sometimes we use this word, something called as regularization. It basically regularize. Basically, do some adjustments, do some required adjustments such that my derivative exists in this case. Because the moment I try to apply my definition of derivative at x equal to 0, turns out that I have this limiting value and this limit exists and this limit exists, and that is equal to, sorry this is written wrong here, and that is equal to 0. So what do I see? The limiting slope at the center of this very tight oscillating function, which you can see here, at the center is like a flat line, as a flat horizontal line, right? You can see from here that's very fast oscillating term. So in the limiting sense, what we found that at very near to the center it turns out to be a flat line. It may be oscillating very tightly over here, but at the center it turns out to be a flat horizontal line. So that's what this particular thing is trying to tell you. So that is an interesting fact. So we have discussed all of this. Now we will move forward to the rules of derivative. If you see the lectures given by professor, he explained various rules of derivatives, where he focus most of his time and attention on this. Let's say you have a composition of function and you just want to calculate the derivative. So we found that the rule which is written in front of you is basically something called as chain rule. Okay, I'm not going to go through the proof and all. Basically, the idea is that in the proof you can see we have two terms here. Like we have this term and we have another term. Like you can see this term and they can see this term. And individual terms basically take place over here. And he also point out that if you see this denominator very carefully, this might be zero, right? So what do I see that this type of definition holds true when you have a non-zero derivative of a g function at that particular input, right? So by avoiding this particular points, you can properly define what you mean by a derivative of a composite function. Hopefully all the ideas are clear, right? Then he came to the idea of this particular identity over here, and this is true only for the first order derivative. Don't do this for second order derivative, that's not true. Let me add a page and write down what do I mean by the idea that my dy by dx is equal to 1 over dx by dy. True, there is no problem in that. But the moment you go with the higher order derivative, like for example second order, this is not true. This is definitely not true. You have to come up with a different idea altogether. So if this is not true, then they are related, right? Then they must be related through some function over here. Through some function here. Can anyone guess what is that function? Or you guys will come up on a next session, for example. Should I discuss here? Or should I give you as an exercise maybe? It would be fun to find out what is this function here. I mean, there is some factor you need to multiply here so that these two quantities are related. This is an interesting thing. Over here I can see it's a direct relation. The factor is just one. But over here they are related. Okay, and at the moment you take another derivative, for example third order derivative, again they are related. Maybe mm-hmm, yes, some another function, some another. Hopefully you guys can find this. Okay, uh, maybe you will find this some in some of your exam, I don't know. I can give you a hint, like how can we find this. Let's talk about this dy over dx square, and I just want to understand how they are related. Okay, so what we can do that we will first calculate this dy by dx, which is actually 1 over. Okay, then we will again take a derivative here with respect to, okay, now with respect to again y. And you can see this is a composition function, right? If you are not clear how these composition functions are, it turns out that my f of x is 1 over x, and my g of x is basically d over dx. Okay, You can see now what kind of composition this function is, and just take a usual derivative. What you will see is a square, and you have another derivative here, which is dy over dy. And you can further go, right? I just give you the direction, like follow this direction, you will get the answer. Okay, next time I'll discuss. Okay, if you have guys any problem, we can discuss this. Now let me see the other ideas. Okay, this maxima and minima, and I'm sure like all of you guys know what do you mean by maxima and minima. And the word maxima minima is very important when you guys try to study something called as optimization, which is the real life example of derivative. No matter what field you study, no matter where you go, you always have a problem in which there are constraints, various constraints. There are the problems are designed in such a way that you have to come up with your best configuration. Best configuration in the sense that you might have that the problem is that you have to use your water less. Using less water, you want to distribute as many as possible. Let's say the idea is that you cannot use. Let me give one simple example. This optimization problem is important. Basically, what happens in the optimization, you have problems which has to do maxima minima. Maxima minima in the sense that you have a function which you want to maximize minimize, because this might be your valuable resource. So if you have a very valuable resource, for example money is a very valuable resource, right? And basically you want to understand how should I distribute my money in such a way that I have a maximum enjoyment. Okay, so you can see over here you have two aspects. Here you have money, your enjoyment, let's say effort. You also want to give less effort as possible, right? So everything is basically encoded in this function, and you want to do some kind of a maximization and minimization to it, such that you have a maximum enjoyment, minimum effort, minimum money spent. Okay, so this idea of optimization comes because you have something called as a valuable resource. If you don't have a valuable resource, then why do you need to optimize? Just do blindly. Okay, but since you're gonna do blindly, things are expensive, you have limited resources, so you have to come up with the best configuration. Like for example, I can give you one simple problem. This is something called as traveling salesman problem, which I'm currently working on. This is one of my research topic. So in a traveling salesman problem, for example, you have lots of cities here. Okay, and let's say you are a delivery person, uh, and the problem is you have to cover all these points in a single path without repeating another. Because let's say you have a delivery package here, let's second, this is second, third, fourth, fifth, sixth, seventh, eighth. I mean, the order doesn't matter. What's the order? But the idea is that you have to come up with a path such that You cover each of them once, and those are something called as Hamiltonian paths. Those who are from computer science, they definitely might be knowing this. Okay, so I have to come up with a path which is shortest and also covers each of the point at once. Like, I mean, at least once, so that I can drop my delivery package. And why am I doing this? Because I'm a delivery man, I'm using some vehicle, okay? So I have a constraint, the constraint of basically of time, right? I have to do things in a as small as time, right? Because time is money, right? That's what we see. And we have something called as a fuel, which again has to do with money. So we want to use as time as possible, as less time as possible, and less fuel as possible. So you have to come up with a problem. You have to come up with an solution. Solution in the sense the path, such that you solve this problem. So this is one of the example of optimization problem. Okay. And in the doing that optimization problem, when you do this optimization problem, when you try to solve this, you come up with a function fx. When you construct the problem, you come up with a function fx where you do your maximum minimum business. Then you come up with an answer, and that answer solution is basically same. So this is your problem over here. So this is what basically I'm trying to say you. The basic idea of optimization. Um, Hopefully that makes you understand. Uh, we have some notion, something called as global minima, global maxima. Then we have something called as a local. So local, global plays a very important role. It depends on what kind of situation you are working on. You might not be interested in the global minimum, but you definitely might be interested in the local minima, maybe local maxima, for example. Let's say, I can give you one example. Why am I saying that? Let me erase this out. This is an interesting problem. Let me give you one simple example. Let's say this is your hill valley, okay? Some hill valley. And you have a ball here. And the job that you have assigned for is to basically take this ball and you have to place this ball over here. But, but you know that, while going from this point to this point, you have to overcome. You have to overcome this barrier, right? Okay, you have to overcome this barrier. Then the moment you overcome this barrier, you will end up over here, right? Then again you have to come up with a barrier. You have to again overcome this barrier. So in this particular kind of problem, you can see you are interested only on local maximas. You're not interested in local minima, because problem is such a way that it automatically finds my minima. The problem is that the ball gets stuck at this local minima because of this barrier. So I have to disturb my ball. I have to give energy to my ball so that it can overcome this particular barrier here. Even though my local minima is here, but still my ball is unable to find that local minima because of these barriers. So the knowledge of local minima and maxima is also important, not just global. Because you might have a problem in such a that it gets stuck here, and you want it to get here. Then I further found that I have another barrier here, which also I have to overcome in order to get my ball here, which is the lowest point, I guess. let's say. So so that kind of a problem you might face, and there is a terminology uh, people use in this world of optimization, that this black line which I have drawn, this hill valley, this is something called as a landscape. Okay, so sometimes, so before solving the optimization problem, you need to know what is the landscape. So in the mathematics, the landscape is given by this function. This is your landscape, and you want to see where is the maxima and minima in that landscape, so that you can play in future with this landscape. Okay, so that's the idea. So from the diagram, from the word itself, it tells you that global minima in the sense, whatever the defined value for which the function is defined, whatever the x for which the function is defined, if that particular x value corresponds to the lowest value possible in my range, then that value, that particular x is my global minima. So this is what actually written over here in a mathematical fashion. Okay, so they can see this y basically tells you all possible, all possible, all possible values which is available, which is over here, and the global minima is basically less than all possible values. That's what's written here. And the definition of the local maxima or local minima is that you basically restrict your input. For example, if I want to study this local maxima here, I will restrict my domain here, right? I'll restrict my input till here, and I'll just study what is the maximum value, minimum value in the function. If my domain, or if I say my defined values of x was that big, then if I calculate what is my maxima and minima, then I see that my minima is here, maxima is here, right? So your minima maxima depends on what values of x you are trying to define. Let me take an example. Let, for example, there is a function fx equal to uh, x square, for example. Very simple example function. Let's say if I define my function from x equal to -1 to x equal to 1, then what do I see? uh, I see that this is my defined value of x, these are my defined curve. Okay, and I see that my maximum values are here and my minimum value is here. But the moment I change my set of input, my whole maximum minima idea gets changed completely. Let's say now my function is defined from here, x equal to half to x equal to 5. Then what do I see? My minimum value is here and maximum value is somewhere here. And this is my defined values. So the location of maximum minima gets changed automatically. So I would recommend you, if you want to find out what are my point of maxima, what of my point of minima, so you have to check values at each and every point, and you have to compare them among themselves. But doing this is not always possible, right? You cannot just calculate values at each and every given x, because that's a very laborious task and you don't have much time, because that will take infinite time, right? Because you have infinite values to check for. So we found some observation. So what is the observation? So the observation tells you that the location in which my maxima and minima occurs. For example, over here, over here. So all these points have a common feature. all these green dots, which are the points of maxima and minima, have a common feature to them, a very beautiful common feature, and that is something called as a slope. The slope, if you try to calculate the slope at that point, basically that instantaneous slope at the point of maxima and minima, this slopes. If you check the slope of all these lines, these are basically horizontal lines, right? Horizontal line, and we know the horizontal line has a slope 0, right? So let's say my this point has to do with A, B, okay, let's say this the set of points. Okay, so what do I see then? Over here, the slopes, the derivatives at that particular location turns out to be 0. All these points. So we came to know that the possibility of maxima and minima is when you try to solve this equation. Basically, these are the locations, possible locations of maxima and minima. But I would also add another set of points. Those are known as boundary points. Like for example, in this example, if you see this red part, right? What I did then, I just changed my boundary, right? My boundary was defined from here to here. But now what I did my definition of boundary from here to here. And in this example, I see that the point of maxima and the point of minima is actually at the boundary, not at that point where the slope is 0. So you see, right? So the possible locations of maxima and minima is, there are two possible locations. One is your boundary point and one is this point. And this point have a very special name, and that name is something called as a critical point. So the location of maximum minima is either at critical point or at the boundary points. And I'm assuming everywhere my function is differentiable. See, I'm not writing continuous, because if my function is differentiable, then automatically it becomes continuous. Okay, so that's my assumption. As far as this assumption is true, I can always check my values of function at boundary points or at my critical points, and I'll just compare them. So what I'll do, I just find my maximum over or the values, and I will say, yeah, that's the maximum. I hope you understand, like values, possible values, maximum. I mean, there's a set, I can always find a set, right? And this set contains basically the values of these particular points. And from that set, I'll select the maximum and then say that that's the maximum value a function can give. So that's the idea. Now the next part of the discussion is how can we know whether I have a point of maximum or point of minimum. I know how to get the locations of maximum minimum, but I don't know how do I distinguish them. How do I know this is a point of maximum and minimum? How can I make sure? So the idea is that we found a trend. For example, if this was my point of maxima and this was my point of minima, we saw that at this location, we calculate slope. No doubt, the slope in this point, for example, if this is x equal to some alpha, right? So a derivative of alpha turns out to be 0. But we see that the slope at just left to this point And if I calculate the slope just right to this point, you can see in this case the slope is negative, and in this case my slope is positive. But over here you can see the green one, the slope is 0. Okay, so what do we see that at the point of maximum my value of slope change. Okay, from the value positive it becomes negative. So if we just see the change in the slope, that basically turns out to be, so the basically the slope of slope, I mean to say, over here it turns out to be negative, right? But in the case of minima, if you see very carefully, the point at the left we have a different slope, point at the minima we have a different slope, and at the point at the right we have a different slope. And over here the slope is positive, over here this slope is 0, and over here the slope is negative. So what do we see here? We see that the slope of slope turns out to be positive. And the way we interpret the slope of the slope is basically a double derivative. So what do we calculate? A double derivative. If that turns out to be negative, we say it's a point of local maximum. We can't say it's a point of global maximum. We can only say it's a point of local maximum, not some global maxima or some rest maxima, because you might have a situation like this, right, in which this is also a point of local maxima, this is also a point of local maxima, but if you compare them, this local maxima is greater than this local maxima, right? This local maxima are at different values, right? So that's why I'm saying that this is basically tells you that particular location. And over here it turns out to be double derivative greater than 0, and that means it's a point of local minima. So that's how we understand in a broad sense like what is happening in these cases. So let me write down this is basically point of minima, and this is my now let's get back to our discussion and let's see what do we see here. So these are just simple meaning, and that's what we saw in this case in the diagram as well. We also saw the idea of critical points. We also saw what do we mean by how to compute the point of minimum point and maximum point. And here is my first step. Just calculate. Here's my first step. Just calculate the critical points, boundary points, and check the values, compare them, and to know which one is point of maximum and point of minima, you just calculate these conditions. So this basically tells me, the condition. Okay, and this is also a condition. So you can check by checking this condition whether this point of maximum minimum or what. Okay. Now we will come to necessary and the sufficient conditions. We know that from here that x prime is my local minima here, or local minima. The way we can say that, the first thing, it should satisfy the condition of being a critical point, because this is not a boundary point. So if I'm claiming that to be a point of maxima and minima, then must be point of critical point, must be critical. Then we check, the derivative at the left. If the derivative at the left is negative and the derivative at the right is positive, then we can say that the slope, the value of the slope, the derivative changes its sign at that critical point, and it changes such a way that the value was negative and turns out to be positive, right? That's why we see that to be as a point of minima. That's what we saw in this diagram as well. Okay, you can see from here itself. So that's what we have wrote here. And the way, and the sufficient condition is this double derivative, and this is what we have shown over here. So this is a sufficient condition to check whether your point is a point of maxima or minima. Now I would like to focus your attention to something called as point of inflation, which hardly people talk about. Inflection. So the example for this point of inflection I would give you to this function, which is fx equal to the x cube, where if you see the curve, it turns out to be this. So this is what your cubic function is, basic, the most simplest cubic function. And you see that this point, this x equal to 0, is my point of inflation. And the reason I'm saying there's a point of inflation, because at the point of inflation we have a change of concavity, but that's neither point of maxima or point of minima. Let me be very clear, this is not point of maxima nor minima. Okay, at that point the behavior is a linear behavior. That's what the point of inflation is, because if over here, if you see very carefully, this was the concavity of this particular part turns out to be concave down, and over here you have something called as concave up. So you can see at that particular inflation point, your concavity of function changes. But if you see very carefully, in the case of point of maxima and minima, you still have that concavity maintained. In the left, you can see it's a concave down, and on the right, you can see it's a concave up. So the concavity of the function is still maintained, and but in this case, you can see the concavity of the function changes. So where the concavity of the function changes, we call that function to be a point of inflation. And if you see very carefully, the way you can find this point of inflation is when you try to calculate a double derivative. The double derivative turns out to be 0. You might have a first order derivative to be some non-zero, but the double derivative comes out to be 0. That's the thing. How we can check this? The double derivative is 0. Okay, so yeah, this is that point of inflation. And why the double derivative is 0? Because the first derivative turns out to be a constant. That means it has a single line. It's like a linear behavior. And if you see very carefully, we see that that's a linear behavior. Okay, so you can see it's a linear behavior. Then the curve of the function change. You can see that. Then the curve of the function change. So in order to change a concavity, it passes through this particular linear behavior. It has to go through this transition through this linear behavior, right? So I will discuss more on this inflation, because whenever you have a point of inflation, your double derivative test, we call all this business something called as a double derivative test. And there are various instances where your double derivative test fails. At that particular point, you have to go to higher order derivative and you have to check whether what is happening. Hopefully you guys don't see that particular situation in your exams. I hope you don't see this. In the next section, we will discuss this numerical analysis, and we will also discuss something called as a monotone and inverse function. For now, I'll just close the session today here. So if you guys have any doubt, please ask me. Okay, you can text me, you can mail me, and you will find this video on YouTube. Thank you very much.